Okay, so this is what we had obtained. Maybe it's time to sum up a bit what we wanted to introduce. For the moment, it was mostly ideas and maybe some notation. All right, so let's say what I'm going to do is to calculate what is called the circulation of a vector field along a curve. Okay, so in order to do this, I need two things. Obviously, I'm going to need a vector field, let's call that V, and I need a curve. Let's call this, usual notations or gamma. Okay, let's be a bit more precise. Let's say that V is a vector field in 2 dimensions. So V depends on X and Y, and itself it has 2 components. Usual notations are P of, P component that depends on xy and q component that depends on xy also. Okay, so that's my vector field. And gamma is going to be my curve. Well, let's say it's described by a parametric curve called gamma of t, which itself again has 2 components, the x component and the y component, both functions of t. That's the, well, let's say typical parametric curve that you studied last year. And we need the t to be between 2 values. Let's call that t0 and capital T and the final one. All right, so the notation for this circulation of a vector field is going to be the following one. We use the usual integral sign on gamma, right? Use the capital gamma or the small gamma. Well, there's a slight difference here. The capital gamma that I've used here, this one, just denotes, well, this is my curve, and I still don't know how it's going to be represented, but then it's going to be represented by small gamma of t, the parametric curve. Anyway, so let's say it's that what we're going to do is this thing, p dx plus q dy. These are the usual notations that are used to denote what is called the circulation of a vector field along a curve. Okay, and so what is that given by? So that should be given by the integral of what we said earlier. So we said earlier that it should be it comes from the dot product between the force, so represented by my vector field, and the displacement. My displacement is actually going to be approximated by the derivative of my parametric curve, so the derivative gamma prime of t, which of course has itself 2 components, x prime of t and y prime of t. So I can make my dot product between that vector v and that vector. Okay, so what do I have? I have the dot product between v and gamma prime, okay, dt. Okay, we need a bit more precision here, right? So there's a notation that I've probably already used, the dot product notation. So you know that dot product can also be called a scalar product. To keep the idea that the result of this product is a scalar value, meaning a real value. So it takes 2 vector u dot product with v. That's the English notation. American denomination takes the it from its representation, so it's a dot. And I like to use this notation. Okay, so 2 brackets, and in between I've got uv, or this one, just to be clear that, well, and the arrows are not mandatory, at least on my side. Just to be clear that what we are doing is not a usual multiplication. All right, so using this, what do I get? I want to do, so v, let's be clear, v depends on x and y themselves depending on t. So I can say that it's v of x of t, y of t. so I'm taking the dot product, the scalar product, with gamma prime of t, which is the vector with x prime of t, y prime of t. Okay, infinitesimal term dt, and then my integration is going to be from t0 to the capital T of that denotes the end of the curve. So, and if we just expand that, we're going to have first component of v is p, second component of v is q, so that we have integral between t0 and capital T, p of x of t, y of t, times x prime of t. This time it's just a product, a usual product. These are two real numbers plus q of x of t, y of t times, that's just the usual multiplication, y prime of t dt. Okay, so what happened here is that I've just expanded my dot product. Okay, so I've got here first component of v times first component of gamma prime plus second component of v times second component of gamma prime. Okay, so that is really my inner product, my product here, right, that I've applied. And this is what we're going to call the circulation of the vector field on the curve gamma of the vector field. Sorry about that. Let me go back. Of the vector field p dx plus q dy. Okay. So maybe we can see just before we do some example, maybe you can see that what do I get here? P is here. Okay, I've got the same P here and here. I've got the Q here and here. So what's left here? I've got the dx, x prime dt, and dy, y prime dt. So maybe it's worth noting that we indeed have something quite consistent. X prime times dt is dx, and y prime times dt is dy. Okay, so it's really like it's really the chain rule. Actually, dx of t is going to be dt times x prime of t. dy of t is going to be dt times y prime of t. Okay, so I guess it's time for an example, right? So before we dig into the example, if we want to calculate this, we need a parametric description of the curve, and we're going to apply this formula here. Okay, so let's do that first example. I want to calculate on some curve gamma that I'm going to describe a bit later, the vector field that has these components, y and minus x. So my vector field, let's be clear, it's going to be given by y and minus x. Okay. So, and the curve gamma that I'm describing is going to be, well, let's say it's going to be a parametric curve with x of t and y of t, and I want to describe the trigonometric circle in the direct sense. So you know that this is just simply going to be described by x is cosine of t and y is just the sinus of t, and for this I just need t between 0 and 2 pi. Okay, so let's do my calculation. So let's say that my integral, let's call that I. So my integral is going to be given actually by, let's apply the formula. So it's p times x prime plus q times y prime dt, and from t0 to t. Okay, so obviously t0 is going to be 0, capital T is just 2 pi, My p, we said, was y of t. Okay, and then we will see what it means. X prime is the derivative of, well, the x we have here, so its derivative is simply derivative of cosine, so minus sinus of t, okay, plus q, okay, so plus q was x, minus x, which we must not forget depends on t, times y prime of t, which is the derivative of the sinus, so cosine of t dt. Okay, so let me just put subtitles here. So that was x prime, that was y prime, and that was x prime of t. That was p, and that was that whole thing was q. Okay, but still I've got the y of t and x of t, but we exactly know what x of t and y of t are on that curve. So let's use that. They are going to be, so integral between 0 and 2 pi. Y of t is sinus of t. So sinus of t times minus sinus of t minus x of t was cosine of t. So cos of t times, well, the cos of t dt. And what do I get? I get, if I expand that, I get minus sine square minus cosine square of t. And so that's just -1 between 0 and 2 pi. So that's minus 2 pi. Okay, that's the value of the circulation of this vector field along the unit circle.